Magnetic fields are created by moving charges. So if you have a particle that is charged in any way and it's moving, that's going to create a magnetic field. So if I've got a positive charge going like this, moving to the right, it's going to create a magnetic field. If I have a negative charge moving up and to the left, it's going to create a magnetic field. That's how magnetic fields are created ultimately, is by moving charges. Now, you may immediately wonder, what about magnets, or what we in physics refer to as permanent magnets? How does a magnet create a magnetic field? After all, it's not like the magnet is moving. It's just sitting on my refrigerator. It's not doing anything, yet it has a magnetic field. Clearly, it's sticking to the refrigerator. So what's going on there? Okay, well, let's look at two situations. First, let's talk about the non-magnet. And what I've got here, this little grid of boxes, okay, each one of these represents, we'll say, an individual atom or molecule in the non-magnet. And so each individual atom or molecule is going to have its own magnetic field. And that's going to come about mostly from the motion of the electrons. So because the electrons are moving, they're going to create a magnetic field. And that magnetic field is going to have a direction for each individual atom or molecule. And so for this first box here, this first atom, that magnetic field might be pointing in this direction. For this next one, it might be pointing that way. I'm just going to go through and draw a whole bunch. Okay. Now, I've only drawn 12. Obviously, if we're talking about something that we would call a magnet, it's got quadrillions of particles in it, if not more. Or I should say of atoms and molecules and such. But the idea is that these magnetic fields, the individual magnetic fields of each atom and molecule, are randomly oriented. And so the overall net effect is that they cancel each other out. So this is why there are non-magnets. The individual atoms and molecules, they have their own magnetic fields because the electrons are moving. And because of that, again, they have magnetic fields, but they're randomly oriented. And so the overall effect is they cancel each other out. Now contrast that with a magnet. In a magnet, the magnetic fields are roughly pointing in the same direction. They don't have to perfectly be pointing in the same direction, just mostly pointing in the same direction. And so they're not canceling each other out, they're building each other up. And so overall, we see a magnetic field. And this is why there are permanent magnets. Not every material is capable of keeping all these magnetic fields pointing in the same direction. There are various factors that go into that, but in general, we only see this in metals, in specific metals, because not even all metals do this. It's only very specific ones that are capable of doing this. So, just to recap, moving charges create magnetic fields. Atoms and molecules can create a magnetic field because of the motion of the electrons, but in things that we do not think of as magnetic, like a piece of paper, they're not magnetic because the individual atoms and molecules, their magnetic fields are pointing in random directions, so they cancel each other out. But in a magnet, they're pointing roughly in the same direction, so they don't cancel each other out. They actually reinforce each other. They build each other up, and we see a net magnetic field as a result. Now, let's talk about another situation. I want to talk about Earth. Earth has a magnetic field. Now, Earth's magnetic field comes about from motion inside the center of Earth. It has to do with the liquid core, the liquid nickel and iron. Its motion, which is referred to as a dynamo, gives rise to a magnetic field for our planet. And this is a good thing because the sun the sun ejects charged particles. These are electrons and protons that are ejected by the sun. We refer to this as the solar wind. And Earth is constantly being bombarded by the solar wind. In fact, everything in the solar system is being bombarded by the solar wind. But, and I should say, this is a form of radiation. If you were exposed to this solar wind long enough, you would die. Okay? These are little bullets. These are little bullets. They're very tiny. Okay? And if they strike you, you won't feel an individual one hitting you. But it can go through and it can hit things like your DNA, the DNA in the cell, and it can cause a mutation. And most of the time, it will cause the cell to die. That's a common one. Or another possibility is the cell could repair the damage. So those are probably the two most likely possibilities, that the cell will repair the damage or the cell will die. But sometimes it causes a mutation and turns the cell into cancer. And when that happens, of course, that's bad. So it's important that we not be exposed to this radiation, to this solar wind, okay? But, as I said, the solar wind's constantly bombarding Earth. So how is it that we are not exposed? How are we protected? And it's because of Earth's magnetic field. Earth has a magnetic field, okay? And it stretches out of stretches out of the poles, the magnetic north and magnetic south poles of Earth. Now you'll notice I did not draw this symmetrically. It's a little flatter on this side, its tail's out on this side. That was intentional. This is how it actually is, roughly. And what happens is these charged particles come in and they get deflected away, because this is what magnetic fields do. Magnetic fields deflect moving charges. So these charges come in and they get deflected by Earth's magnetic field. And so they go past us as a result. And we are not constantly bombarded by the solar wind. We are protected because of Earth's magnetic field. And let me say, this is a big issue for space travel. How do you protect astronauts from the solar wind? You know, they're out there for a long period of time. They're exposed to this. How do you protect them? That's a big issue with space travel, trying to do that. Now, the magnetic field doesn't actually prevent all of these particles from reaching the surface of Earth. Sometimes one might be energetic enough it can still go through and hit Earth. But more common is that they go around, and this will be explained in another video that I'm posting that somebody else has made on YouTube. But essentially, these particles, sometimes they get trapped in the magnetic field. And when that happens, they end up spiraling down they spiral down the magnetic field line toward the magnetic poles as a result. And this gives rise to the aurora borealis and the aurora australis. So those are the northern lights and the southern lights. And as I mentioned, I'm posting two videos that I found on YouTube, one that kind of goes more into the detail of how the aurora come about, and another one that just actually shows the aurora, because it's really beautiful if you've never seen it before. And the light that comes off is actually because these particles, these solar wind particles, come down and they collide with molecules in the air. It's a very energetic collision, and as a result, light is given off.